Welcome to the Blueprint Room. Now, today we are acting as chief architects, and our singular mission is to engineer an absolutely unshakable foundation for Cambridge AS and A-Level Math 9709 Kinematics. Listen, if you've ever felt like your understanding of mechanics is resting on incredibly shaky ground, you are in exactly the right place. We are going to construct a load-bearing, highly analytical argument that survives the most rigorous examiner stress testing. Now, in my time as an exam structural engineer, I see two types of builders out there on the exam site. First, you've got builder one. Let's call him Alex. Alex loves to stack up massive, heavy bricks of raw facts and complex equations without ever checking if his underlying steel frame can actually support the weight. He just dumps the numbers on the page and hopes for the best. Then you've got builder two. Let's call her Sam. Sam is all about the aesthetics. She wants to put up shiny glass panels and decorative features using fancy terminology and elegant handwriting before she's even cemented the foundational columns. She completely misses the core command words. Both of these structures look great for about 5 minutes, right up until the Cambridge examiners bring out the wrecking ball. Today, we are fixing that.
Let's start with a hard truth, straight from the Cambridge Principal Examiner reports. They state, quite clearly, that kinematics is one of the most misunderstood areas in mathematics. Think about that for a second. Many exam structures completely collapse right here. Students often build their answers on fundamentally flawed assumptions, confusing their basic building materials, and as a result, their entire mathematical skyscraper comes crashing down. But we're going to show you exactly what the site inspectors, the examiners, are looking for, so your grade stands tall and proud, totally immune to the stress points that take down thousands of other candidates.
Here is our project schematic for today's build. First, laying foundations. Second, the method mark framework. Third, the processing protocol. And finally, avoiding structural collapse.
Phase 1. Laying theoretical foundations.
Okay, the Cambridge syllabus explicitly insists that we secure our theoretical architecture first. You simply cannot build a skyscraper on a foundation of sand, and you absolutely cannot solve complex kinematics problems without knowing exactly what your core materials are made of. Examiners report time and time again that candidates consistently confuse key terminology. Using the wrong term is literally like finding a massive crack in your foundation concrete. So we must cement our first foundational block right now: distance. Distance is a scalar quantity. It represents the total length of the path traveled, regardless of which way you are pointing. Think of it as the raw amount of ground covered. If Alex runs around a construction site randomly laying down 500 meters of cable, the distance is 500 meters. There's no specific direction, just the raw, unstructured magnitude.
Now, contrast that scalar concrete with displacement, which is our load-bearing vector beam. Displacement indicates your exact position relative to your starting origin. It requires both magnitude and direction to function properly in an equation. Let's go back to our builders. If Sam walks in a giant circle around the site and ends up right back where she started, her distance, the raw effort she put in, might be the whole circumference of that circle. But her displacement is 0. She hasn't structurally moved from the origin point. When you're writing extended responses, you must define this clearly. If you treat a vector beam like a scalar brick, your equations will snap right down the middle under the pressure of positive and negative axes.
Next up on the drafting board is speed, which simply measures how fast our mathematical structure is moving along its given path. Because it is directly based on distance, speed is also a scalar quantity. It doesn't carry any specific directional stress, it just tells you the rate of change of distance over time. It's like knowing the crane is moving at 10 meters per second, but having zero idea if it's swinging toward the building or away from it. It's useful data, sure, but it's incomplete for structural alignment.
But velocity? Velocity is where we finally add directional alignment to that moving beam. It is the rate of change of displacement over time. This is the crucial vector counterpart that you must clearly distinguish from speed before using it in your framework. This is precisely where so many students, just like Alex and Sam, bleed marks on the exam. They treat velocity like it's just speed, without accounting for the fact that a velocity can be negative if it's moving in the opposite direction along an axis. You have to honor the direction, or your calculations will lead you completely off the blueprint.
Finally, we have acceleration. This acts as the dynamic force fundamentally altering our velocity beam. It is the rate of change of velocity per unit of time, and it completes our 5 essential foundational blocks. Here is the structural rule. If your velocity is perfectly constant, your acceleration is 0. There is no dynamic force changing the beam. But if the direction of your velocity changes, even if the overall speed is identical, you have acceleration happening. You are applying force to turn that beam, and you must account for it mathematically.
So with the basic terminology poured like fresh concrete, we have to ask a critical site audit question. Why do these mental structures crumble the second examiners change the testing environment? Let's look at the foundational challenge. Cambridge examiners intentionally design high-tariff questions to test the exact assessment objectives, the building regulations, if you will. They want to see if you can transfer conceptual understanding to unfamiliar contexts. When a problem doesn't look exactly like the standard textbook example, the weak foundations suddenly crack. It comes down to command stress points. For instance, if an exam question commands you to evaluate a kinematic model and you simply describe what the model is doing, you've built a descriptive structure instead of an evaluative one. You've basically built a nice wooden shed when the examiner specifically asked for a steel bridge. The structure instantly collapses under the weight of the mark scheme criteria because you didn't align your paragraph columns with the actual blueprint instructions.
Phase 2. The Method Mark Framework.
In Cambridge exams, the procedural framework holds up the structure, not just your final number. You are awarded crucial method marks for the process itself. If you just magically write down an answer with absolutely no working out, you're essentially handing the examiner a floating roof with no structural walls to support it. I was at the drafting board with 2 students yesterday, our archetypes, Alex and Sam. They were having a massive ironwork peer debate about a high-mark paragraph. Alex wanted to fill the whole paragraph with a massive cement block of terminology definitions, just stating what acceleration is over and over. Sam argued that without leaving a hollow space for a dynamic counter-argument or showing the mathematical steps, the structure has zero flexibility to hit those top-band scores. And Sam was somewhat right. Here's the exact procedural blueprint they needed and the one you need. Step 1. Extract the relevant data from texts and tables. Step 2. Select your analytical framework. Which kinematic equations actually apply here? Step 3. Execute the analysis with incredibly clear, logical notation. And Step 4. Present your findings using the precise terminology we just covered. Deconstruct, extract, execute, and present.
The absolute most crucial point here is that referencing cross-topic connections and showing your systematic working is exactly how you rivet your raw data to the final evaluation. When Alex and Sam hit an unexpected structural roadblock mid-paragraph, where their evidence being totally failed to latch onto their main thesis column, I had to step in with a structural blueprint template. We adapted the Peel methodology for math: principle, extract, execute, link. State the kinematic principle, extract the data, execute the calculation visibly, and link it back to the specific context of the question. The principal examiner reports consistently highlight that candidates who show this kind of evidence-based, step-by-step reasoning achieve significantly higher marks. Your method literally is your structural integrity.
Phase 3. Processing and Presentation Protocol.
Look, it is one thing to have the right numbers in your head. It's another entirely to present them on the page so the examiner can clearly verify your architecture. Presentation follows incredibly strict conventions, and ignoring them is a spectacularly easy way to lose credit. This standardized sequence matrix you see right here is your ultimate processing protocol. Consider this your mandatory site safety checklist. First, identify key elements and given information. Isolate the variables. Second, apply the relevant kinematics principles and write down the formula you're using. Third, execute your analysis by breaking it into logical, sequential steps with clear workings shown on every single line. And fourth, always verify your results for reasonableness and present them with proper headings, units, and clear formats.
When the blueprint calls for a comparative analysis between 2 different kinematic models, say comparing the velocity of 2 different particles, you must explicitly identify both similarities and differences. This is where builders like Sam often fail. They build half the bridge by pointing out how the models are similar, but they totally ignore the stress joints, the differences. You have to lock them together using comparative connectives, support each comparison with hard numerical evidence from your calculations, and then draw definitive conclusions about their relative impacts.
Phase 4. Avoiding Structural Collapse.
Okay, everybody, helmets on. It is time for a mandatory mid-build site inspection. We need to look closely at the examiner warnings from past papers to avoid a complete structural collapse on exam day. These are the specific reoccurring pitfalls that trap hundreds of candidates every single year. But right before we pour that final layer of text concrete to lock in your knowledge, you need to make sure your long-term construction line is permanently reinforced. I need you to hit that subscribe button for Ace the Exams at the handle @AceTheExams right now to receive our weekly structural grade upgrades. Picture a heavy industrial hardhat clicking a giant metallic subscribe button, locking your academic foundation into place. Whether you're building an IGCE foundation or erecting an A-level skyscraper, this channel is your primary support grid all year round.
All right, let's dive into an interactive viewer rebar stress test. If I put a complex source data chart on the screen and gave you a 60-second visual countdown timer,
Could you extract the single most high-yielding core metric needed for construction without falling into the classic traps? The principal examiner reports reveal the top 3 reasons these structural beams fail under pressure. Number 1, answers are simply too vague. Examiners demand specific, mathematically backed details, not general sweeping statements. Number 2, format and presentation are completely ignored. When an examiner sees a chaotic jumble of numbers with no clear annotation or logical flow, they cannot award method marks. And number 3, answers lack context-specific details. You absolutely must tie your pure math back to the physical reality of the specific problem given in the prompt.
To reinforce your answers against these specific failures, you must constantly evaluate the quality of your evidence. In complex kinematics problems, you must explicitly identify any limitations or underlying assumptions you made during your calculations. Think about the hidden flaws in the concrete. Did you calculate a trajectory assuming air resistance was completely negligible? Did you build your entire equation on the assumption that acceleration was perfectly constant the entire time? Stating these assumptions out loud in your answer proves to the examiner that you truly understand the physical system and its boundaries, not just the abstract algebra. State your assumptions and your structural integrity skyrockets.
Here is a fantastic structural upgrade for your exam toolkit, a little memory hack you can take with you. Create a personal acronym for those 5 core foundational factors: distance, speed, displacement, velocity, and acceleration. Having a snappy, memorable acronym ensures you mentally check off each concept as you read a problem. It guarantees you will never forget to explicitly define your terms and separate your directional vectors from your scalar quantities before you even start crunching the numbers. It is a simple tool, but it prevents massive foundational errors.
As we finally clear the drafting board today, I want you to lock in your 3 primary structural takeaways from this workshop. First, master your precise definitions and understand exactly how scalars and vectors interact. Second, prioritize the method mark framework. Your systematic step-by-step working is just as important as the final answer itself. And third, always build your mathematical arguments within the specific real-world context given by the question.
Let me leave you with one final rebar stress test to think about as you walk off the site today. Imagine you're finished the exam. If your final calculated number at the bottom of the page is absolutely perfect, but your procedural framework, your method, your logical steps, your clear notation is completely invisible to the person grading it, will your exam grade actually survive the examiner's rigorous stress testing? The historical evidence from Cambridge says no. A floating roof with no walls will always crash down. So build smart, follow the blueprint, show your working, and I will see you back here for the next explainer.